If you're watching this video and you don't yet have a good understanding of how SPI works, I would definitely recommend checking out my previous videos where I take you through the basics of SPI and how to implement an SPI Master both in VHDL and Verilog. This video builds on that knowledge and shows a real application of the ambient light sensor project, instantiating an SPI Master. So go back and check those out if you haven't seen those yet. The purpose of this project is to show you how SPI works inside of an FPGA, and to really demonstrate that, what I have chosen to do is to connect an ambient light sensor to an FPGA, which communicates over an SPI interface. And I'll show the demo first to show you how it's working, and then we'll talk about why it works and details. So here is the FPGA board. This is a Go board, which are available from my website, nanland.com. And as you can see, the segments are a little bit dim right now, but if we hold up a light to, like my flashlight, for example, to the sensor, the lights on the 7-segment displays grow a lot brighter. And if you cover them up completely, they go out. So uncovered, covered, uncovered, covered. And as you bring your light closer and further apart, it's able to sense varying degrees of brightness. So it's dim, bring your light closer, it's much, much brighter. That is the ambient light sensor running on this little board over here. This is the FPGA board, the Go board. And if you want to test this out yourself, you can go to, there's two things you need. First thing is the ambient light sensor PMOD board itself, which is available from Digilent. They make a lot of these PMOD boards. They're kind of handy, they're not too expensive, and you can test out different peripherals with them. So great way to just kind of plug and play and try different things out. And so that's the first thing. The second thing is the Go board itself, so nanland.com. And then the Go board is a link right here, so you can buy it right there. Neither of those things are required. You can simply follow the tutorials in this tutorial, and you'll be able to get the project up and running as well. But it is fun to see some things running on hardware, so I do recommend it. So the Go board itself, it's an FPGA. There's a single PMOD connector on the side here, and that's what this is. That's what this is running right now. So here's the PMOD connector hooked into the board. The PMOD chip is this ambient light sensor chip. Simple SPI interface, so chip select, NC, no contact, my favorite, SDO, serial data out, SCK, the clock, ground, and VCC. So this actually doesn't have any data being sent back to the FPGA. It's only a one-sided data transfer. It's just data into the, I'm sorry, other way around. There's no data going into this chip. There's only data going out of this chip. So the data out is the actual binary encoding for how bright it is. So it's seeing some brightness, and it's digitizing that brightness and serializing it and shipping it out to the FPGA. And it describes how it works and everything. It uses a VHDL semiconductors. This is the brightness sensor chip here. So this generates an analog voltage that corresponds to how bright the ambient room is. So that's this little guy. It's pretty hard to see actually, but there's a little guy with a clear top that has some silicon that's able to sense brightness and generates an analog voltage corresponding to the brightness. And then the ADC chip, which is the analog to digital converter. Again, SPI is a super common way to interface with analog to digital converters, and here's an example of that. Here's an ADC by Texas Instruments, and I think this will take me right to the datasheet, yeah. Analog digital converter takes in an analog voltage, digitizes it, and ships it out over some interface. I2C, SPI, or some common, or some custom interface are very common. So here's the ADD converter. It's all built into the PMOD chip, all these voltages and things. What we care about is this. We care about the serial timing diagram. So this is how fast does the data change, and what mode does this operate in order to make it work correctly. So we have chip select going low to initiate a transaction. There's a 2-byte transaction. So 3 leading data bit zeros, 8 data bits, 4 trailing zeros. That's how this guy works. And then there's some time when the chip select goes high between reads of the ADC. So we have to look up this parameter to know how much to set our dead time to. And what else is important here? I think those are the big things. Oh, the mode of the SPI. So does it even say what mode it's in? This is by far like the most painful part of this stuff, is like trying to figure out what mode things are even operating in. What mode did I set it in the code? I set it to mode 3. So I set it to mode 3, so clock polarity equals 1 and clock phase equals 1. So you'd have to look to see at this when the data is changing relative to the clock in order to figure out your clock phasing. And your clock polarity, it looks like it idles high because it's high at the beginning, and this actually kind of throws me off a little bit because at the end it goes low again. So this must be the beginning of the next transaction, that's why. So yeah, clock phase is definitely high. Clock polarity is definitely high, so it's idling high by default, and the phase of when the data changes relative to the clock is equal to 1. So that's the most painful part. And if you're ever confused, you compare this waveform to like the SPI timing. I have this like shortcutted because I look at it so often, especially when doing these projects, that okay, what is it? And just look and compare and figure out which mode your chip is in. Because they don't often say like, this is mode 2, which would make things so much easier if they did, but they don't. They're like, yeah, you'll figure it out. You're smart. So there you go. You do need to look up this chip select parameter here, which is in usually like the timing parameters inside the data sheet. Let's see if we can find it real quick. I'm doing this on the fly, so apologize. Timing information, where are you? Must have gone by it. Let's go up. I did go by it. Okay, here you go. So minimum chip select pulse width is 10 nanoseconds. That's pretty small. We don't have to worry about that too much. What did I set it to in the code? Inactive clocks. I set it to 100 clock cycles. I think that was an arbitrary choice. You can sample as fast as you want from an ADC. This is a really slow ADC, so it actually doesn't really matter how quickly we sample it because it's sensing brightness, and like it's a human thing. Like the human's actually looking at this brightness. So even if I'm sampling at 10 kilosamples per second or 10 samples per second, honestly, it won't even make a difference because your eye can't really tell the difference how quickly that data is actually changing inside of from the readback. So if we're getting this byte, so the data that's actually coming back to us is just a single byte, and that byte corresponds to the brightness. And I forget if 0 is bright and FF is dark, or 0 is dark and FF is bright. We're going to dig into the code and we'll figure that out. Let's see, what else is there to say? That's the ADC. Here's the PMOD chip. There you go. This is a better view. Oh. That's the brightness chip right there. That's the analog digital converter. Super tiny stuff. Really, really small. Pretty cool. The Go board, we talked about that. And I think we're ready to dig into the project. So I'm gonna do it both in VHDL and in Verilog. In interest of keeping just one video for both, let's do the what do I have open? This is VHDL. Let's do VHDL first. I'm going to do VHDL first, and then we'll talk about Verilog after that. So if you're interested in Verilog, just skip this section or watch it and learn a little bit about VHDL. Either way. All right, Ambient Light Sensor project for the Go board. This interfaces to the Digilent PMOD Ambient Light Sensor, which we just showed there. Uses SPI to receive 3 bytes from the PMOD board, not 2. Don't listen to me. The SPI operates at 2.5 megahertz, and here's the format of the data. It looks like, is that a typo? Now I'm confused. We're going to get into it. All right, MSB, the 3 leading bits are 0. That was from the data sheet on the analog to digital converter. 3 leading bits are 0. Then you get D7, D6, D5, D4, D3, D2, D1. Fixing this as I go. D2, D1, D0, and then the last 1, 2, 3, 4 are 0, and this one I guess is Z for high impedance. So yeah, why they chose to do this, I'm not really sure. You know, if you have 8 data bits, why not just put it in a single byte instead of like spreading it arbitrarily across 2 bytes? Good question. I asked that same question. I have no idea why the ADC works this way, but it does, and so that's the way we wrote the SPI code interface too. It's kind of nice because it gets to stress the chip select, the multi-byte transactions, and all that stuff, so we can show cool stuff instead of just being a single byte transaction, which is less interesting, but this is more confusing, so trade-offs. Okay, the 7 segment outputs are here. Those are all going to be driven to the same value to drive the brightness of it. The SPI interface is there. We have SPI mode 3 based on the ADC 08S021, which is the ADC on the PMOD board. Clocks per half bit is equal to 5. This is generating an SPI clock. This is actually something you should look up in the datasheet too for whatever you're doing. So the Go board, for example, operates at 25 megahertz. Usually there's an upper limit on SPI frequencies for your ADC, for example. They say like you have to be under 5 megahertz, maybe between 100 kilohertz and 5 megahertz, something like that. Usually not much more than 10 megahertz and starts to not work as good after that. You can always run slower. It depends on your application. So some signals. SPI Master with single chip select. Here's the code that we've been talking about. Instantiated, very good. Here is handle read requests from ADC. Just request data as often as possible. Sounds good. So whenever the master TX is ready, which is the output of this SPI Master chip select, whenever that's ready, we're just going to go ahead and request another one. So we're going to pulse data valid. So this thing is constantly being stressed. Ready, go to work. Ready, go to work. No breaks. And we're going to have an LED counter, and I'll talk about that in a minute. So that's just a counter that counts up to the width of it, which is a byte. So it'll count 0 to 255 over and over and over and over. Forever. Basically, whenever this thing is plugged in, that thing is counting. Okay, so handle data being read back from the SPI interface. So pack up a response into a single 8-bit data value. This is... So if this is making use of the RX count index, it's handy. So we get this RX count indexed of the received byte, and based on that received byte index, we know where to look in this data. So we know where in the ADC word, which is the full 16 bits, to put the received byte. So if the received count is 0, meaning it's the first byte being received, then we drop it in the most significant byte spot. If it's the least significant byte, if RX count is equal to 1, then we drop it in the least significant byte. And now that I'm looking at this, I'm pretty sure I set the count to 2. Yes, always 2 bytes per chip select, which means that my description is wrong. It should be 2 bytes from the PMOD board and not 3. That's a typo. There we go. Fixing this as I go. This is great. Okay, we're receiving 2 bytes. Here's byte 1, index 0. Here's byte 2, indexed 1. To confuse you further. Okay, the ambient value itself is the actual byte that we want to drive, that we're getting back from the analog digital converter, and it's using bits 12 down to 5. And again, if you go up to here, this is 12, 11, 10, 9, 8, 7, 6, 5. Perfect. 12 down to 5. That's where that comes from, and we get this. So we get a byte. So this is the byte. This is what we've been working for this whole time, is just to get 8 data bits off of an ADC. That's all we want to know. We got it. All right, awesome. What do we do with it? Well, okay, we have some byte that corresponds to some brightness, and it looks like the LED, okay, so 0 is off, 255 is max brightness. Thanks, past Russell, for writing comments. Helpful. All right, so when this thing is at 255, the ambient value is at 255, that is the most amount of brightness that the photo sensor dude is seeing. We are counting up via this LED count, which just runs continuously, and we're basically comparing it to this readback value. And so if the readback value is 0, then LED count is always going to be greater than 0 most of the time. So we're going to set this to, we're going to have this else condition. If the ambient value is FF 255, then LED count's almost always going to be less than that, and the LED enable is going to be set to 1. So most of the time the LED is going to be enabled. What this is doing is it's generating a duty cycle effectively, where it's driving the LED with pulses very, very quickly, and those pulses can be really short or they can be really long. And to the human eye, if you were to put an oscilloscope on each one of these pins on the 7-segment display, you'd actually see tons of pulses being driven. But the effect of your eye, your eye can only see it, so slowly that it actually just filters out all those pulses when you're looking at it. And so it looks just dim, looks a little bit dim. And if I cover it up, it goes off, and I uncover it, goes on. That's actually, I'm changing the pulse width right now by doing this, but your eye is able to filter all that stuff out and just shows a brightness indicator. So it looks brighter when the duty cycle is higher, and it looks dimmer when the duty cycle is lower. It's a handy trick with all LEDs. It's a way to dim and make LEDs that kind of look like they pulse, like they have a heartbeat to them almost, instead of just like on off. You can have them like become brighter, become darker, become brighter, become darker, and that's all just done by varying the duty cycle. Handy trick, I use it here. This LED enable gets inverted based on the way the 7-segment displays work, and I just send it to every single segment on the Go board in order to give a cooler representation. You can route. I originally had it mapped to these 4 LEDs, and it just wasn't as captivating as when you send it to the 7-segment. So send it to the 7-segment. It's pretty nice. All right, that's the VHDL code. I'm going to talk through the Verilog code quickly here. See if we can go through it quick. Verilog time for all you Verilog friends. Skip this if you just watch the VHDL. Here we go. All right, Verilog code. We are going to be, the whole purpose of this whole thing was to interface to a single ADC on this guy and get a single byte off of that ADC that determines the brightness of the ambient room. And here's the way it looks. We have, oh boy, I have the same typo. Okay, I'm fixing my stuff here. We're receiving 2 bytes from the PMOD board. The SPI is operating at 2.5 megahertz. Clock phase equal 1, clock polarity equal 1. Here's the data coming back. This is specified in the ADC datasheet. So the first 3 bits are 0. Here's the actual data. And then these trailing bits are all, we don't care about those. We only care about these guys right here. Cool. Here's your input. This is just, iSwitch 1 is just the reset for this. So if you hit this button, it'll reset it back to a default state. Here's the FPGA clock. Here's your 7 segments. Here's the SPI interface. SPI mode is 3. That's based on the part itself. That's what. So I said this is a local param. SPI mode 3. Clocks per half bit equals 5. So we can operate the ADC at any frequency really, as long as you're operating. Usually there's an upper bound to the frequency of the ADC that you can operate at. So this just sets some frequency that works for that particular part. CS in active clocks is equal to 100. This is the time between transactions, just to have inactivity on the line. Local signals, boom. Here's the SPI Master with single chip select functionality. We hard code this ITX count to 2. So there's always 2 bytes going out because we're interfacing with one ADC chip for this project, and it always needs 2 bytes, or always gets 2 bytes back from it. We're never going to do variable byte lengths, so hard code that guy. We have some signals around it, and what this is doing is just requesting data as often as possible. So whenever the master is ready, we're just going to send data valid to it and just drive some data on it. So that is maybe worth talking about. The data going out is always going to be 0 because the ADC doesn't actually get any data from us. It'll just get dropped. But this code will be shipping zeros out of the MOSI line, even though the ADC doesn't care about it. but it does, that's how you kick off the transaction. So data valid gets pulsed there, and here is where we take the received byte coming in from the MISO, master in slave out, MISO, and we're going to make a 16-bit word. This is the ADC word. So if the receive count is equal to 0, then it's the most significant byte. If the receive count is equal to 1, then it's the least significant byte. So we build up the 16-bit word, which corresponds to the 16 bits up here. Then we need to know where in that 16-bit word do we actually even care about the data. And I can tell you it's 5, 6, 7, 8, 9, 10, 11, and 12. Those are the bits that we care about, which are going to be right here. There we go. So drop the first 3 bits and the last 5. ADC word 12 down to 5. That's the money. That's what we're looking for. All this whole effort was just to get 8 bits off this ADC, and now we have them, and I'm happy about that. Here's the ambient value. This is what it's all about. Ambient value of light in the room. All right, so 0 is off. If that ambient value coming back on the ADC is 0, that means that the ambient is off. And 255 is the maximum amount of brightness that it's seeing, that it's possible to see. And what we're doing here is we have this LED counter that just runs forever and ever, and that's an 8-bit counter. Reg 7 down to 0, so this will just count from 0 to 255. And the ambient value also is a 0 to 255 value, and if the counter is below that ambient value, then we're going to be enabling the LED to drive. So at a low ambient value, the LED enable will be off most of the time. For a high ambient value, the LED enable is going to be on most of the time. Similarly, in a bright room, in a dark room, it's off. In a brighter room, it's on, and there's the values in between. The brightness can go up and down. That's it. The LED enable gets sent to all the 7 segments, and this inversion here is just done because the way the Go board's wired up requires an inversion there. But that's it. That's how you get the information off the ADC and drive a varying duty cycle pulse on your LED. I guess it's worth mentioning. So I said this in the VHDL section. I'll say it again here, which is that if you're driving an LED with a duty cycle pulse, so it could be a small pulse, it could be a wide pulse, but it's happening a lot of times every second, your eye basically filters that out. And so what you see as kind of a dimmish value is actually maybe a 25% duty cycle wave being driven to these LEDs, but it's happening so quickly that your eye just filters it out and just sees a dimmish LED. Similarly, if you have a really bright thing, it would be on more often, and that just makes the LED look brighter. So this is a useful trick that is used a lot of the time for driving LEDs. If you're just driving it on or off, it'll look like pulse. Like let's say you want to do a 1-second heartbeat timer, right? You could do on, off, and that would look fine. But it would look cooler is if you set up a duty cycle, varying duty cycle, where every 1 second it would go from its minimum brightness, minimum duty cycle to 100% duty cycle in a second. So it would have this glowing effect, almost like a heartbeat, where it would like get brighter, get darker, get brighter, get darker, and it looks like it's more of a pulsing heartbeat thing, which is really cool and totally worth all the time and effort it takes to make that happen. So I recommend you do that for all your LEDs. But yeah, that's the same effect we're using here, basically. All right. So I'll just run quickly through how this is all programmed. I use IceCube 2, add your design files. So this is the light sensor ALS. This is the top of the project. SPI Master, we should be familiar with that. SPI Master with chip select added in. That should all be familiar as well. Have to add some constraint files, which just, this is a clock constraint, and then we also have physical constraints. This is an IceCube thing. If you're using Xilinx or if you're using Altera, whatever you're using, you'll have different constraint files. You'll have a different FPGA. But if you want to just follow along with this one, you can get the Go board, and you can just follow this here. There's a lot more tutorials for the Go board in general, so it's kind of nice. So we run this, we generate a bitmap. This has already been done. The output of the bitmap then gets programmed via this programmer. So here's the light sensor ALS bitmap.bin. We click the program button. Boot to boot to boot. Spins a while. seconds for a long while. There it goes. Erasing, programming, operation successful. So there we go. We have a fully programmed, brand new FPGA build running on the Go board, doing some ambient light sensing. So I hope you enjoyed this project. It's a lot of effort to get data off of, a single byte off of a single chip. SPI is used all over the place though, so you do it once, you understand it once, and you can leverage it, reuse it, and it's a lot easier the second time. So that's the end of the project. I hope you enjoyed it. Hey, I just wanted to jump in at the end of this video real quick to say, please check out patreon.com/nandland and consider supporting me there. I would really appreciate it. It helps me cranking out these good tutorials and these videos. So if you found this valuable, consider heading over to Patreon and supporting me. Keep me making good content. In addition to that, please consider getting yourself a Go board so you can actually program this code and try it out on real hardware. They're available at nandland.com. And thanks for your support.